Hello everyone. I welcome you all in the third lecture on rolling contact bearing. In the previous two lectures, we have covered various aspects of rolling contact bearing like their classification, their application areas, their drawbacks, their advantages, and the factors that affect their selection. In today's lecture, we intend to cover or understand the actual selection procedure of rolling contact bearing from the manufacturer's catalog. At the end of this presentation, students shall be able to understand which rolling contact bearing is to be selected for a particular application, how rolling contact bearings are designated, what is the selection procedure of a particular rolling contact bearing from the manufacturer's catalog, how rolling contact bearings are selected for cyclic loads, and in the end, how rolling contact bearings are selected for exceptional reliability. We covered in our previous lecture that rolling contact bearings are not designed but they are selected because design of rolling contact bearing is complex and complicated. So designer's job is just to make sure which of the available rolling contact bearing from the manufacturer's catalog will be suitable for application. Definitely, to have that know-how, we must follow some procedure, and that is the objective of this presentation, to lay down a standard selection procedure of rolling contact bearing from the manufacturer's catalog. Before going into the details, it is worth mentioning that we should know that how rolling contact bearings are designated, because whatever comes in standard form, they have a particular designation. So a rolling contact bearing is designated by sometimes 4 and sometimes 5 digits. The last 2 digits indicate the bore diameter in millimeter. Bore diameter divided by 5. For example, if the bearing number is XX15, that means if we multiply the last 2 digits 15 by 5, then bore diameter comes out to be 75 mm. So simply looking at the last 2 digits of the bearing, we can be sure that this bearing will be suitable for a particular shaft diameter. For example, if the last 2 digits of the bearing are 10, that means the bearing is suitable for a shaft diameter of 10 into 5, 50. Or in other words, the bore diameter of the bearing is 50 mm. That doesn't mean that if last 2 digits are 00, then it will be suitable for a shaft diameter of 0 mm. So there are 4 exceptions of it also. If the last 2 digits are 00, then the bore diameter is 10. If they are 01, it is 12. If they are 02, it is 15. And if they are 03, it is 17. And from 04 onwards, the rule, that is last 2 digits multiplied by 5 will give bore diameter shall prevail. I think you have understood the point very well. So it's very important to know the designation. So we have talked about last 2 digits. Now coming, the third digit from the right indicates load series of the bearing. For example, if the third digit is 0 or 1, that denotes extra light series. Third digit 2 denotes light series. 3 denotes medium series, and 4 denotes heavy series. You can see the diagram. There are 4 bearings in it with series 60, 62, 63, 64. These are first 2 digits of the bearing. You can see all the bearings are having same internal diameter. So they are meant for the same shaft diameter. But they are arranged in the increasing order of their load carrying capacity. So our job is to find which of the available bearing will be suitable for our application. So we have talked about 3 digits. Now remaining 4 digit or sometimes 5 digit from right specifies the type of rolling contact bearing. They are being assigned on the part of manufacturer. They are free to give some suitable number as per their manufacturing capabilities. For example, if the digit is 6, this denotes deep groove ball bearing. Now, with this information, I think we are able to predict what bearing 6309 means. It simply means that if as last 2 digits are 09, so it is suitable for a shaft diameter of 45 millimeters, 09 multiplied by 5. Third digit from right is 3, so it is suitable for medium series bearing. It is medium series bearing, so it is suitable for medium loads. And last digit is 6, that means it is a deep groove ball bearing. Now, before going into the selection procedure, we have seen in our previous lectures that there are few factors that affect the selection of rolling contact bearing. These are static load carrying capacity C0, life of bearing L10, which is life for 90% reliability. Then dynamic load carrying capacity C, equivalent dynamic load P, and load life relationship. We have seen all these factors in detail in our previous presentations. It is worth mentioning that C0 and C will be available in the catalog. P is something which we need to find from the given value of radial load and axial load, and life of the bearing we can predict from the catalog or data book. And then there is load life relationship, which will be used to solve get into the final details. So let us selection procedure of rolling contact bearing. The very first point is we need to calculate radial and axial loads and shaft diameter if not given. In majority of the cases, we'll be given these loads, radial load, axial load, and shaft diameter. If not given, from our knowledge of shaft design, we need to find what will be axial load, what will be radial load, and what will be the shaft diameter. Now, the next part is selecting a suitable bearing. Like there are plenty of options. There are ball bearings, there are roller bearings, there are needle bearings. So depending on what are the loads, radial load and axial load, we'll select bearing for our application. This table provides the guideline for selecting a bearing. We have covered this in our previous lecture also. If ratio of FA by FR is less than 0.7, single row deep groove ball bearing will work. If ratio is greater than 0.7 but less than 1.5, double row deep groove ball bearing will work. And if the ratio is more than 1.5, any rolling contact bearing, be it roller bearing, be it needle bearing, be it angular contact bearing, be it self-lining bearing, will work. So in the first two steps, what we have done, we have calculated radial load and axial load and shaft diameter if not given, and then we have fixed which particular bearing is to be used, either ball bearing or roller bearing or needle bearing. Then in the third step, we need to calculate equivalent dynamic load P, which is given by x VFR plus y FA, where FR and FA are already known to us. V is race rotation factor, which is taken as 1 when inner race rotates and 1.2 when outer race rotates. X is radial load factor and Y is axial load factor. So it is very clear that to be able to find P, what we require is value of X and Y. Now, when we move on to finding the value of X and Y, what we are encountered with is a table like this where value of X and Y is given. But to be able to enter into this table, we require FA by C0. And we know C0 is something which is given in the data book or catalog. So that means we need to find C0 for a particular bearing from the catalog, and then we can enter into this table to find X and Y. What does that mean? That means that this selection procedure is done by trial and error method. Means we have to assume that this is our bearing. We have to start with that, and then we'll see whether the bearing is suitable for us or not by adopting the procedure that we will discuss in the coming slides. So by this time, what we have found what is radial load, what is axial load. We have selected which bearing is to be used, and for finding P we need X and Y, but for X and Y we require FA by C0. So what we have done is, when we go into the table, we see that values of C and C0 are given for different bearings. You can see the bearings are arranged in the increasing order of their load carrying capacity. All the bearings are suitable for a shaft diameter of 40 mm because the last two digits are 0, 8. Third digit is 0, 2, 3 and 4. That means they are arranged in increasing order of their load bearing capacities, and 6 denotes they are deep groove ball bearing. This is obvious that the bearing which is meant for a light series will be less expensive than the bearing for medium or heavy load series. So we'll start with the light series bearing. We'll use this as our bearing and take C0 from C0 as 9300, and then we start calculating the ratio FA by C0 and find X and Y. Comes the table again. Now since we have selected, we have as a first trial we have taken bearing as 6008, and we know what is C0 for that bearing, so we can find FA by C0. Say it comes out to be 0.070. For this, value of E is some factor 0.27. Now we need to find whether this set of X and Y will be applicable for us, or this set of X and Y will be applicable for us. For that, we'll see our FA by FR. If it is less than or equal to E, this set will work. If it is more than E, this set will work. So what we have done, we have tried first bearing 6008, found C0 for the bearing, then entered into this table, found FA by C0, and then depending on the ratio FA by FR, whether it is less than E or more than E, we found what is X and Y. So that enables us to determine equivalent dynamic load, which is XFR plus YFA. So for the bearing 6008, our C0 is known, and we have found what is equivalent dynamic load for the given radial and axial loads. Now we will take the decision about the Elton life. Elton life, which is the life for 90% reliability. either it is given in hours or it is given in million revolutions. If we are taking this as our life, we need to convert that into million revolutions. If it is, we are assuming life from this table, we need not convert that into million revolutions. So next step will be to find this L10 equals to C upon P raised to power P, where P is some constant which is 3 for ball bearing and 10 by 3 for all other bearings. In this equation, L10 is known to us. P we have already calculated. The only unknown left is C, which is dynamic load carrying capacity. And P we have fixed in the very first step when we have selected which bearing, either ball bearing or roller bearing or needle bearing are to be used. So from this equation we can find what will be C. Now we need to check whether this C which we have calculated is more than the C which is stipulated for the first trial bearing or less than the value of C which is there in the first trial. Suppose C comes out to be say 18,000 18,000 newtons, but actually the bearing is having C as 16,800 newtons. So this bearing will not be suitable for us because we require our bearing to have a dynamic load carrying capacity as 18,000 newton, whereas in actual the bearing is only having dynamic load carrying capacity as 16,800 newtons. So what we'll do? We'll move on to next bearing 6208. We'll again find the ratio FA by C0, again find X and Y, again find P, and then again find C. We'll continue this procedure until the C that we have calculated comes out to be less than the C which is tabulated for the selected bearing. I think you have understand the procedure. Let me revise it once again. We'll find FA and FR, then we'll find which bearing is to be selected, that is either ball bearing or roller bearing. Then we'll find equivalent dynamic load. For that we require X and Y. X and Y can be found only when we have the ratio FA by C0. So we will use the trial and error method. We'll go to the table, take the C0 of the light series bearing, and then for the ratio FA by C0 we'll find X and Y, then we'll find P, then from the load life relationship we'll find C, and we'll check whether this C which we have calculated is less than or greater than the value which is tabulated in the catalog. We'll do the exercise until we get this relation. C calculated should be less than C tabulated. Now, since our C is different, say in third or fourth step, our C tabulated is 20,000 newtons and C calculated is 18,000 newtons. That means this bearing is safe for our application. So we'll find the life, L10 life again for the C which is tabulated value. Obviously, the life will come to be more than what is the desired life. So this was the selection procedure of any rolling conduit bearing from the manufacturer's catalog. Now, one more situation arises in which the load, be it axle load, be it radial load, they are not uniform, they are not constant, they varies. For example, there can be an application in which radial load is this much of Newton at this much of RPM for 25% of time, then this much of Newton at 900 RPM for 50% of time, then 1000 Newton at 1000 RPM for remaining 25% of time. Now, to address such situations, we are having one particular formula which is like this. By using this formula, we can go on to the same selection procedure that we have done for the applications where load was constant. This formula says that PE is equivalent dynamic load, is cubic root of N1 P1 cube plus N2 P2 cube plus N3 P3 cube and so on upon N1 plus N2 plus N3. What is P1, P2, P3 and N1, N2, N3 over here? Here P1 is XFR1, P2 is XFR2, P3 is XFR3. Since there are only radial loads, we have taken FR1, FR2, FR3. If there are XL loads also, P1 would be XFR1 plus YFA1, P2 will be XFR2 plus YFA2, P3 will be XFR3 plus YFA3. So we can find it. I think it is clear. Now what is N1, N2 and N3? They are revolutions. They are not RPM, they are revolutions. Like assuming the cycle for which this load is being applied to be of 1 minute, then it is revolving at 700 RPM for 25% of time. That means in a cycle of 1 minute, it will be 15 seconds. So in 15 seconds, it will revolve for only 175 revolutions. So N1 will be 175, that is 700 divided by 4. Then for the remaining 900, it will revolve, the revolution will be 450, that is 900 by 2. Why 2? Because it is for 50% of time. And for 1000 RPM, it is 1000 by 4, since it is for 25% of time. So it is 250 revolutions and so on. So by usual procedure, we'll find P1, P2, P3 and N1, N2, N3 and we'll find PE. Now instead of the in the load life relationship, earlier it was L10 C1 P raised to power P. Now we'll put this PE, which is equivalent of equivalent dynamic loads that we have calculated, and the remaining procedure will be same as that for the bearings where load was constant. One more situation will arrive. Before that, let us define reliability of bearing. Reliability is defined as number of bearings successfully completed L million revolutions upon total number of bearings under test. So if it is 90% reliability, that means 90% of the bearing of the group have successfully completed L million revolutions life. In many cases, there is risk to human life. So it becomes necessary to select a bearing having reliability of more than 90%. We have whatever formulas we have used there L10 life, which was life for 90% reliability. So in such cases where desired reliability is more than 90%, we'll use a different approach. The relationship between life and reliability is given by a statistical curve known as variable distribution. You can see over here that as reliability is increasing, the life of bearing is decreasing, and as reliability is decreasing, life is increasing. So it is there is exponential decay in the life as reliability increases. For variable distribution, this formula with this relation will holds true. Reliability is given by e raised to power minus L by a raised to power b. A and b are constants. L is life of bearing, R is reliability. Assuming L50 average life equals to 5 times L10 life, we can find easily what will be A and B. So A for this condition is 6.84 and B is 1.17. Now what we'll do, we'll use this formula. This is an extension of what we have done in the previous slide. So say we have been given reliability as 99% and life for 99% is given to us. To be able to adopt the procedure or to able to use the load life relationship, we ought to know what is L10 life. So we'll put this L life given to us for say 95% reliability. We'll put R95 as 0.95, R90 is 0.90, A and B, we have found. So we'll found L10 from here, which will be more than the life which is given for 95% reliability. We are doing this because our formulas load life relationship is based on only L10 life. So we'll do that. We'll find L10 from here. We'll use the load life relationship, and the remaining procedure will be same. There is one more variation. In a system, if there are n bearings, each having a reliability of R, then the complete reliability system shall be given by R raised to power n. So in this presentation, we have tried to understand the standard selection procedure of rolling contact bearing. By adopting the procedure, we'll be able to select any rolling contact bearing for the given application. We'll try to solve some numericals also following the same procedure. Enjoyed the presentations. We'll continue with the same in our next presentation. Thank you so much for your patient hearing.